In our last video, we saw that a map of the U.S., or any other map that satisfies a condition that a state is a connected region, it could be colored using four colors, at most four colors. It was the four-color theorem. Only four colors are required to color any map drawn on a flat surface. We can formalize that by defining planar graphs. So a graph that can be drawn, that can be, not that it has to be, but that can be drawn on a flat surface without any edges crossing, we call it planar. And so if we were to consider a complete graph on four vertices, K4, we often think of it as this. It is possible to draw that graph so that no two edges cross. Right? So we could do that. So instead of drawing the edge from those two corner vertices, we could draw that edge on the outside so that it avoids crossing that one on the inside. So K4 is planar. K5, a complete graph on five vertices. Let's see what would happen if we tried to draw this so that none of the lines, none of the edges crossed. So we could draw this out here. We could draw in here, from here to here, from here to here. We still need an edge from this point to this point. If we go on the inside, we'll cross those lines. So let's go out and around. We also need an edge from this point down here to this one over here. And so we could draw that out and around. Are we missing anything else? And yes, we are. We're missing from this point. No, we're not. What are we missing? 1, 2, 3, 4. 1, 2, 3. We're missing from this point. This has degree 3 to this point. So if we go on the interior, we're going to cross this line. If we go on the exterior, we're going to end up crossing this line. So no matter what we do, we are going to have a line that crosses. So K5, it is not planar. Great. So that's a planar graph and non-planar graphs. If we were to think about states being vertices connected by an edge, if they share a common boundary, then the map coloring is equivalent to the graph coloring. So if we were to look at that map of the U.S., we could take some of those states. So here we have Oklahoma, Texas, so pretend this is Texas, and I guess Louisiana is somewhere over here. So we have these states. We could convert these states to just points. So this is now a single point. This is now a single point. This is a single point. This is a point. This is a point. And this is a point. And then we have edges between 2 points if they are adjacent. And so these here, if I were to draw this a little bit better. These states here, they're adjacent. Those are adjacent. They share a border. Shares 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 a border. Those share a border. And what we end up with here is we do end up with this nice planar graph. If you look at just the pink stuff, if you were to imagine deleting the actual states themselves, you do end up with a planar graph. And so the four-color theorem in graph theoretic terms says if G is a planar graph, then chi of G, the chromatic number, is no more than 4. We can color it with 4 colors or fewer. Let's look at another example. Here we have a water gas light graph, a K33, a complete bipartite graph. Think about having 3 houses. 1, 2, 3. Each one of those houses needs to be connected to water. It needs to be connected to gas. And it needs to be connected to light. And so the question is, can we run lines to these houses without any of these lines crossing? So water from water, we have it going to house 1. Maybe from water, we have it going to house 2. And from water, we have it going to house 3. From gas, we could go here to house 3. That gas line's going to have to go out and around to get to there. It could go around that way. You might see that we're already going to encounter some problems for light. We could go around that way. We could go around that way. Or, I don't know, maybe that's not the best route. You could go around this way to get to that one. But getting light to this house is going to be difficult because we already have that house fully surrounded by other lines. Right? So these other lines completely surround that house, and so when we try to run a light line to it, it doesn't matter where we go, it's going to have to cross a line somewhere. So is this K33, that water gas light graph, is that a planar graph? The answer is no, it is not planar. And what that looks like here, a K33 in general, if you were to draw this without regard to crossings, this is how we often draw that K33. Just like that. Great. So it turns out that a graph is planar if and only if it has no subgraph that is homeomorphic to K5, a complete graph on 5 vertices, or K33, that complete bipartite graph. And when we say homeomorphic, we're really saying there's no part that looks like. It does not have embedded in it somewhere this K5 or K33. So if you were to look at something like K6, a complete graph on 6 vertices, this complete graph on 6 vertices, we could restrict our attention and say, well, right here, these 5 vertices right here, and the edges connected to them, or at least a subset of those edges, does actually give us K5. So we see K5 showing up in here. K6 has a subgraph that looks like K5. So it is not planar. So K6 is not planar. Great. And so any complete graph with more than with 5 or more vertices is going to have K5 as subgraph. But you don't have to have a complete graph, right? So let's say I have something that looks like this. So even there, even though I don't have a complete graph, I can see it has K5 as a subgraph. So it's not planar. There are some real-world applications of graph colorings. You can deal with it for conflict resolution. So when you have scheduling conflicts, vertices can represent committees. You connect 2 vertices with an edge if they cannot meet at the same time. And then you assign meeting times as colors. A proper coloring will give you a schedule for meetings without conflicts. Channel assignments, you can have your vertices for like radio. Your vertices are broadcast transmitters. You connect 2 vertices with an edge if they're within 100 miles of each other, and then you assign colors again appropriately. All right, next time we are going to look at chromatic polynomials. We will see you there.